Warning: all our videos are made only for educational purposes and to demonstrate scientific laws that we verify. These experiments must be supervised and we are not responsible for an incorrect execution of an experiment done by others. We do not encourage in any way that you misuse our experiments to do violent things and harm others.
Hello everyone, welcome back to Games by Destiny. Today we are going to start a new series and we are going to examine the theoretical part of chemistry.
In particular, we will try to post more often this theoretical video, and also we want to ask you that if you have some exercise that you want us to do, we will be glad to make a particular video in which we will solve all these exercises.
Many of you might ask themselves, why do molecules exist in this universe? In fact, some may say that atoms are enough stable by themselves, but that isn't true. In fact, matter seeks stability. So what does it? What do atoms do? For example, hydrogen, we don't find it in the form H. This atom isn't found in nature. Instead, we find the biatomic molecule H2 because it is more stable. What happens here is that a bond between the two hydrogen atoms is formed, and we indicate the bond with this line. But what does the line actually indicate? It actually indicates that we have two electrons that were put together in order to gain stability. In fact, what we actually had in the beginning is these two atoms of hydrogen, of which everyone had one electron, which put together their electrons in order to gain stability. In fact, this is the line that we saw, and this is our bond. So why exactly two atoms, exactly two electrons were put together? We know that there are actually some atoms that are stable by themselves. For example, these atoms are the noble gases. Noble gases, for example, helium, or neon, or xenon, and other gases, other elements like this, which have a peculiarity. In the case of helium, its most stable form is given when it has two electrons. And so hydrogen, which tends to arrive to this form, only needs a single bond in which two electrons are put in conjunction. But in another case, which is that of neon, we see that here another atom, for example oxygen, which has 6 electrons in its most outer shell, actually tends to do something else. As you know from the electron configuration, hydrogen has a configuration of 1s1, in which we have only one electron in its most inner electron shell. Instead, the helium has 2 electrons in this shell, and neon has the following configuration, in which we see that there are 8 electrons in its most outer shell. Oxygen by its side, it has a configuration of 1s2, 2s2, and 2p4. So it lacks 2 electrons in order to gain a stable configuration. So it tends to take these 2 electrons from another atom. A very common reaction could be that between calcium and oxygen, because in this case oxygen needs 2 electrons, which can be provided by calcium, because in order to obtain the most stable configuration, it gives 2 electrons. Another gas is, for example, helium or neon, and all of these elements are very stable, and that is why they are called like such. And what they have different from hydrogen or any other compound, any other element, is that they have their outer shell of electrons that is completed. That means that if we take, for example, neon, this is the nucleus, and around the nucleus we will find the various electrons. These electrons are probably found in an orbital. This, for example, is the 1s orbital, and here we're going to find two electrons, and there is the outer orbital, which is the p, the one. This is 2s orbital, and then we also find the 2p orbital, and neon has all its atoms filled in this orbital. So in p it has a total of 6 electrons, and this is what we know as the electronic configuration. For example, another atom very near to neon is oxygen, for example. It has an electron configuration of 1s2, 2s2, and 2p4. What this means that it's in its most outer shell, the 2p shell, it only has 4 electrons, and because of that it needs to gain more electrons in order to be stabler. So this is what happens in the bond between hydrogen, the bond between two atoms of hydrogen, and what they do is they share these two atoms, these two electrons, in order to form a bond in which both of them have completed the octet. In the case of hydrogen, we see that the nearest noble gas is helium. In fact, this is an exception. So hydrogen tends to arrive to the electronic configuration of helium, which is only 1s2. But the other atoms, like oxygen, it tends to rise to the nearest configuration of the noble gas. So in this case, instead of 4, it tends to arrive to 6. So what do we have to say next is that this representation is the structure of Lewis. If we take an atom, we can represent its most outer shell with these dots or other with lines. So for example, if we take oxygen, we know that this is its configuration, and its most outer shell is the current one here. So to represent all of these atoms, we need to electrons, we need to represent 6 of them. So this is oxygen, and we have 1, 2 dots for the S2, 1, 2, 3, 4. For the P4, we can also present them in this way, but the most important is the number of the electrons. So it needs another 2 electrons in order to complete the octet. So that's why oxygen by itself isn't stable. In fact, similarly to hydrogen, it makes it is a bimolecular, it's a biatomic molecule. In fact, we see that oxygen is found in the form of O2. That means that the 2 atoms of oxygen are bound to each other. But differently from oxygen, we have a double bound. That's why, because they need 2 more electrons in order to complete their octet. Instead, hydrogen needed only 1. So this bond, we see that it's something like this, for example. Before the bond happened, we know that this is their current form. So the 2 frontal electrons go and form a bond. Then these 2 electrons are transferred here, and they also form a bond in this form. So the final result is a double bond between oxygen and between the 2 atoms of oxygen. And we said that we can also indicate it with lines. A line means there are 2 atoms, 2 electrons there. So after this, we might see that the atoms not only combine with their similar, so we don't see only hydrogen combining with hydrogen or oxygen combining with oxygen. We can see also that oxygen can combine with hydrogen, and this is the common molecule that is water, H2O. So H2O is a very particular, molecule in which it has this structure, and here we have two free pairs of electrons. What has happened here that hydrogen has shared one electron with oxygen, and also that the other hydrogens shared also another one. So in the reaction we can see two things, or in a case like this, hydrogen and oxygen share their electrons, they share their free electrons, or we see in a case such as, for example, sodium and chlorine. They don't share their electrons, but the electron is taken from chlorine, and what forms after this are two ions. These are the two ions that form in the reaction, and this here, when they share a bond, this is a covalent bond, but instead when they the one atom gives the other one an electron, this is a ionic bond. In this ionic bond, we see that the two atoms are held together by the forces between the ions, which are governed by the law of Coulomb, which is the current law here. And so we can see another difference in this case. So the first thing that we can note is this compound will be less stable, for example, of this one here. That is because magnesium has two spare electrons to give to oxygen. In fact, it is found in this current form here. And so the number of charges that are present in the crystalline structure are more, so the force is stronger. In fact, this one has a lower boiling fusion temperature, which is at around 800 degrees, and the other one has a similar boiling temperature. So what happens during a reaction is that the fact that some cases the electrons are shared, in another they are taken from one atom. It depends of the electronegativity of the two atoms. As we know, for the periodic table, where it is written, there are the atoms like fluorine or chlorine or oxygen, which have a very high electronegativity, and there are other atoms such as sodium, hydrogen, also we may say lithium, generally the metals on the left of the table, they have very low electronegativity. So this one here tend to take electrons. Instead, these tend to give their electrons. So this is because they have a very great difference of electronegativity. But in other cases we see that that's not the case. For example, there can be atoms with similar electronegativity. For example, carbon and hydrogen, their electronegativity is pretty much the same. And for example, this compound is very stable, that is methane, and because the electronegativity between the atom of carbon and hydrogen is almost the same. In another case, this is ionic. This forms a ionic bond. This one forms a covalent bond, but there is also another one that is the polar bond. For example, we have this molecule, which is hydrochloric acid. Hydrochloric acid forms a polar bond, which is a way in between, because this one is very great. It's very big, the difference of electronegativity. Here not, but here it's somewhere in the middle. So what happens is that the electrons here, we know that they share two electrons. The most of the electrons go near the atom of chlorine. So that happens because it is also much bigger. We might represent it in this way. And most of the electrons come near the atom of chlorine and not of that of hydrogen. So there is one last bond that we have to discuss, which is the metallic bond. In this case, a metal, for example iron, its atoms are bound in a different way. All the electrons that we find can circulate in the crystalline structure. In fact, we see many of the nucleuses, for example protons and neutrons, which are firmly put into the structure, and we also can see some of the electrons that are free to flow wherever they want in the structure, of course not going too far away from their nucleuses, but here the electrons aren't fixed to a particular atom, as we saw in the other cases.
So guys, the video is over, and obviously we want you to know that in particular this video must be accompanied by a more deep study, maybe with your book or with something else, because this video is not enough to understand this theoretical part of chemistry.
So everyone, if you like this video, please let us know in the comments, and also if you want to answer some questions. So if you want to see more amazing videos and also experiments like this, go visit the page and subscribe to it. So for today is all.
Thanks for watching.